Hello, everyone. My name is Taro Shimizu, and I'm a postdoc at MPE. And on behalf of the Gravity Collaboration, I'm very excited to give this talk on the central parsec of 3783. Now, here in this talk, I'll be discussing the subparsec gas structure and kinematics around a very nearby AGN. And in particular, we'll be studying three different regions. The broadline region at 0.01 parsecs, two, the hot dust at 0.1 parsecs, and finally, the coronal line region at about 1 parsec. All of this is detailed in a new publication that has just been submitted for publication. And you should be able to find it on arXiv in the next coming months. So as I mentioned, we'll be using gravity. And here, what gravity is a second generation instrument on the Very Large Telescope interferometer that combines the light from all four of the UTs to get simultaneously 6 different baselines. This gives us a resolution of only 3 milliarc seconds in the K-band at 2.2 micron. But really, the greatest advantage and the greatest success of gravity is its vastly improved sensitivity, which allows us to use interferometry on very faint objects. And here in the bottom left, I show a highlight from our paper in 2018, our first observation of the AGN 3C273, where we were able to spatially resolve the broadline region and show that it's composed of clouds in a rotating thick disk. Now in 3783, we're able to do the exact same thing as in 3C273. And what we're specifically using is spectral astrometry, which looks at the differential phase instead of the absolute phase. So we're referencing to the hot dust continuum. And so across the broadline region emission line, shown here at the top in the black data points, we see a characteristic S-shape of the differential phase, which indicates that the emission region is rotating. And so using our broadline region model and fitting both the flux emission line profile as well as the differential phase, we can get different parameters for the broadline region. In particular, the size of the broadline region we find is about 71 micro arc seconds, or about 16 light days. We find an inclination of around 25 degrees and a black hole mass of around 7.7 solar masses. And I invite you to watch Shan Guan's talk, where he discusses possible implications for at least our size measurement and place it on the so-called radius luminosity relation for broadline regions. Now, secondly, we are able to produce an image of the hot dust continuum around the AGN. And what we find are 2 different sources in the image. One, our primary source, which has a full width half max size of about 0.13 parsecs. And interestingly, a secondary offset source about 0.6 parsecs away that has around 5% of the total flux. Now, our primary explanation for the secondary source is that it's a massive gas cloud heated by the central AGN. Number one, it seems to be well within the ionization cone of the primary AGN as deduced from our broadline region model based on the inclination and position angle of the broadline region. And secondly, we find that we would need about 20 solar masses of gas within the source that's emitting at a dust temperature of around 600 K to produce a K-band flux. And so going from 20 solar masses to a density of around 10,000 per cubic centimeter does not seem to be an unreasonable density for gas that's in the very central regions of an AGN. So it is only with gravity that we're able to spatially resolve the secondary offset source from the primary hot dust around the AGN. Now, finally, we are also able to study the coronal line region, which composes of very highly ionized emission lines, and in this case, the calcium-8 line. And so across the calcium-8 line, we see a strong dip in the differential visibility amplitude, which indicates that the coronal line region is much larger than the hot dust continuum. And we also see a dip in the narrow bracket gamma component, which probably means that this narrow component is also being produced in the same region as the calcium-8 line. And so by modeling both of the differential visibility amplitude profiles and flux profiles for both lines, we find a coronal line region size of around 2.2 milliarc seconds, or 0.4 parsecs, one of the first size measurements for the coronal line region. So in summary, we find that gravity is providing a very unique view into the subparsec environment around AGN. And in particular for NGC 3783, we were able to study 3 different regions: one, the broadline region, 2, the hot dust continuum, and finally, the coronal line region. And in our paper, we discuss how all of these structures are working together, and we provide a very comprehensive picture of the circumnuclear environment around 3783. So I invite you to read the paper when it comes out on the archive. Thank you.